Alright, now we're going to tackle something called implicit differentiation. So, first it helps to understand what the difference between implicit and explicit means. So, if we can take a function y and write it as a function y equals f of x, where basically we're saying that we have y and the only thing we're writing it in terms of is things involving x, whether it be the cosine of x or x squared or x cubed plus cosine of x plus 1 over 3, something like that, then we say that y is given explicitly. In other words, it's solved for y. If we cannot do this, then we say that y has been given implicitly. Or we cannot or have not solved for x. So we know that we have y as a function of x. We just don't know what that function is. And so as an example, we're going to go ahead and try to calculate the derivative of y with respect to x of this equation. So we want to go ahead, and since this is something where we have x squared plus y squared equals 25, which is the equation for this circle here. I know it doesn't look like a circle, but that's just because the axes are a little squished. This is something where if we try to solve for y, we're going to have y equals this plus or minus square root of something. And so that's not going to be something we really want to do. So this is going to be one of our implicit definitions for y. So here, what we want to do is we want to calculate dy dx or y prime. And when we calculate this, we're going to have to use y in our definition of trying to solve for y prime. So we're going to basically take the derivative on both sides of the equation and then try to algebraically get y prime by itself. So the question is, where does y prime end up coming from? So step one is to take the derivative of both sides. So in other words, we're going to take the derivative with respect to x of x squared plus y squared and set that equal to the derivative with respect to x of 25. So something that we had mentioned when we had first started taking derivatives is when we're saying we're taking the derivative with respect to x, what this means is that x is our variable here. And so remember that somewhere in the back of our heads we know that y equals some function of x. So when we take this derivative, the derivative of x squared we know is 2x. However, we don't know the derivative of y squared. So this will actually be a chain rule since y is actually some function of x. So essentially what this is right now is y squared is some function of x squared. So by trying to take the derivative of this with respect to x, we're going to do a chain rule where the outside is x squared and the inside is f of x, or in this case y, which we know is some function of x. Now the derivative of the outside is 2x, and the derivative of the inside will be whatever y prime of x is, or just y prime. And so this is what we're going to use when we take this derivative, is we'll use this chain rule. So it'll be plus 2, replace the x with the inside function y of x, so 2y, times the derivative of the inside, which is y prime, so 2y, y prime, and then the derivative of a constant, which is 25, equals 0. So we've taken the derivative of both sides, so step 2 will be to solve for y prime. So the first thing we're going to do is we're going to subtract over the 2x. So we'll have 2y prime equals negative 2x. And then we'll divide both sides by 2y. And so we'll get that y prime equals negative 2x divided by 2y. Or in other words, y prime equals negative x over y. So again, we don't actually know what y is. We're not sure what that function is. However, once we do know that we can find its derivative by plugging in the y. This could eventually lead to things like finding differential equations, which is a much more advanced topic. But this is one of the things that we'll have to do. So if you're trying to use implicit differentiation, you'll start off with your equations. You'll take the derivatives on both sides. If there's a y in there, remember that's a function of x, and so you'll have to be careful about chain rules and things like that, and you'll keep going from there. So we'll see a few more examples, and then after these next two examples, we'll go ahead and let you guys find or try some more examples as exercises. So let's say we wanted to find dy dx, which again is just y prime if x cubed plus y cubed equals 6xy. So if we're doing this, remember it can be useful to think of these y's as being f of x's. So we're taking the derivative with respect to x on both sides of x cubed plus y cubed and setting that equal to the derivative with respect to x of 6xy. Now note that x and y here, since they're both different, they're both functions of some kind, this is actually going to require a product rule. So both functions, so use product rule. Alright, so when we go to find this, we'll have 3x squared plus 3y squared times y prime. So note here that when I just got into 3y squared plus y prime, the derivative of x squared is 3x squared. The inside function is y, so it's 3y squared. But then the derivative of that inside is where we get that y prime from. And so this will be equal to 6 times the derivative of this when we get our product rule. So we can factor the 6 out to the front. And so we'll get x times the derivative of y plus y times the derivative of x, which is just 1. And so we get 6 times the quantity x times y prime plus y. And so this then leads us to 3x squared plus 3y squared times y prime equals 6xy prime plus y. So at this point, what we're going to want to do is get everything that has a y prime on one side and everything without a y prime on the other side, and then factor out y prime and solve for it. So we'll subtract over the 3x squared, and we'll subtract over the 6xy prime. So we'll have 3y squared y prime minus 6xy prime. And that'll be equal to y minus 3x squared. Or sorry, 6y. Why didn't you guys tell me that I had made a mistake? Oh, it's because right now you're just a figment of my imagination? Yep, that sounds about right. Alright, so again, don't make the same mistake I did. Make sure you distribute the 6. And then from here we'll factor out a y prime. So y prime times 3y squared minus 6x will be over here. And on the right we'll still have 6y minus 3x squared. And so dividing over, we find that y prime equals 6y minus 3x squared divided by 3y squared minus 6x. And so again, we don't necessarily know what this function y represents, but we do know that if we did know what it is, we could plug it in to find what the derivative of y was with respect to x. Alright, so say we wanted to go ahead and find the equation of a tangent line at a particular point 3, 3, for example. What we would do is we would find the slope with our y prime. So slope at the point 3, 3. We already know our formula for it. It's 6y, which is 3, minus 3x squared, which is 3, over 3 times y squared, so 3 squared, not on the page anymore, minus 6 times 3. And so if we take in the numerator, 6 times 3 is 18, minus 3 times 3 squared, we get negative 9. And then in the denominator, if we take 3 times 3 squared minus 6 times 3, well, that's just going to be a positive 9. And so we'll get negative 1 as the slope. So then remember, our equation for a tangent line is y equals mx plus b. And we don't know what b is, but we do know what the slope is. And we do know one point on the line. So we'll have 3 equals negative 1 times 3 plus b. So 3 equals negative 3 plus b. So if we add the 3 over, we get that b equals 6. And so if we were looking for the equation of the tangent line for this equation, we would be looking at y equals negative x plus 6. Alright, so we have another example where we've seen implicit differentiation. We have an example where we found our equation of a tangent line when we have implicit differentiation at a particular point. What's going to be on the last page of these notes then are 3 more exercises for you guys to try. So just to see you're getting in the habit of it. And again, if you have questions on this, when the scanned version of the notes are up, these will be on there. So you'll see the work, you'll see the answers, and then you also are encouraged to ask questions about them on the discussion boards, in office hours, ask me questions, and all of that.